All right, what I want to start doing here today is I want to put up these things for us to try to name so that we can get a little practice with that. We have a little bit of extra time. I'm slightly ahead for various reasons. I think one of the bigger ones is that I actually do get that extra hour with you guys that I don't in a normal semester for lecture because I don't have to take up class time for tests. But I thought it would be useful to spend the time to go over some more nomenclature stuff, maybe look at a few more reactions before we get to the activity series and the solubility rules, because there was a question before lecture about using that activity series from your lab manual. So what I'm going to do is hit the pause button and give a whole bunch of dead air for a few minutes while you guys try to write the name of, or the symbol, sorry, of the name and the name for the symbol. And then I'll pop back on in a couple minutes, hit the record button again so that people watching this don't have all that dead air. So without further ado, we'll pause. All right, we've had a few minutes here. So I'm gonna go ahead and start in. Calcium nitrate. Who had an idea on that one?
I just started with Ca and then N. That's all I got.
Okay. Well, you know the N's going to be there. So, but remember, nitrate is an NO3.
Would it be?
Go ahead.
Would you need 2 of the nitrates?
Yes, that is correct. We know that calcium is a +2 from the periodic table. Nitrate, one of those ones we're getting together with to sort of get to know. So if you're a little slow on that, that's totally fine. We've only known this for a couple of days. We're gonna have to practice a lot for the next few. So, okay, the next one, ammonium phosphate. Looks like Maria has a mic up. She's all antsy for this one. Look at that. She just disappeared as fast as she came up there. Look at that. The ammonium phosphate. Does anybody have an idea on that?
NH4 with parentheses around it because you need 3 of them, and then PO4.
That's correct. Ammonium with that +1 and phosphate with that -3. So you need 3 of the +1s to match it. All right. Let's see, Frank's got his mic up. Did you get an iron sulfate there for me, Frank?
Dude, I didn't even get that far.
All right, that's fine. Anybody else besides Miguel? Otherwise, I can do this with Miguel, but because he's all bold and strong there. Anybody else want to give their hand at this one?
The iron sulfate.
Yeah.
FeS.
FeS, but remember sulfate is an SO4. When it's all by itself, if it's just an S, that's sulfide standalone. When we have the SO4, that's the sulfate.
Okay.
But you're on the right track because you got that sulfur thing going on. And it is a 1-to-1 because I said there was an iron with a +2 and the sulfate is a -2. So those will balance each other out straight up. Sulfuric acid. Anybody got a sulfuric acid? Ooh, Maria's back up. I think that's accidental. All right. Sulfuric acid is the one that takes that SO4. It's H2SO4 for sulfuric acid. Hydrobromic. Frank, what's the hydro mean?
With water. So
Right.
it's like,
Okay. And it's an acid, so what does it start with? Help me help
hydrogen.
you. There you go. And I wonder what the next one's going to be. Bromic.
Bromine.
That's right. And since they're 1-to-1, there you go. All right, this should be the good one here. Cadence, what do you got for phosphorus trichloride? Okay, no Kalins. Ellen, did you change your moniker? You used to be in blue. Now you're green. That's weird.
Not sure what happened.
Huh. I don't know what I mean,
Oh, it's
Miguel's
me. Is it PCL3?
yeah. These are the easy ones, guys, because they tell us exactly who and how many. These are the nice guys to us. So then dinitrogen tetrasulfide, Giselle.
Oh boy. I know it's gonna be a nitrogen
There we go.
with a 2.
Okay.
Physical 2. And then 3 sulfides?
4.
4.
Just like tetrahedral had 4 sides, tetra
Oh,
means
that's right. Not 3, but 4. Got it.
right. Alex, what about this magnesium chloride? Oh, all right. What about, oh, Laura.
Would it be MgCl3?
Mg with a Cl and a 2.
Okay.
Magnesium is in the second group, so it's a +2. Chloride or halogen has that -1. Okay. So I'm going to slide it over here so it's easier for me to write. 1. What did you think of this FePO4? Well, we know that there's an iron, and that PO4 we know is a phosphate because we see it right there. Oh, there's a chat. What's happening in chat? Someone tell me. This story says, don't call on me.
It's just old stuff that's not relevant right now.
Okay, PCl3, got it. So we know it's an iron and we know it's a phosphate. The phosphate has a 3-. Since there's only one of the irons, that must be a 3+ to balance it out. So that is now iron 3 phosphate. We look at V2O5. This is an ionic compound. We know we're going to sandwich their names together, but vanadium does not behave as a transition metal. So we have to say who it is. So we know our pieces are vanadium and oxide. Question is, what do we put in here? We know oxygen is a 2-. 2 times 5 is 10. The vanadium side must be a +10. We have 2 of them there. So it's vanadium 5. Jackie, what'd you get for SO3?
SL3.
Yes.
PL3. SL3.
SO3.
I'm just kind of listening.
Okay, that's fine. I'll tell you, I'll put you on the do not call list. Did I have, was Lisa here? Lisa, right? Where's Lisa on the do not call list? All right, so when you get in here, what's SO3 going to be?
Just kind of going how we've been going. I'm thinking like some type of sulfur oxide.
Yeah. There you go. We know it's a sulfur, and we know there's an oxide. But now this is 2 nonmetals, okay? So instead of numbers or numerals and stuff like the Roman numeral, we have to now rely on the Greek prefixes to tell us how many. 2 nonmetals is going to Greek. So 1 sulfur, not a problem. We leave it alone. 3 oxides would mean it is trioxide. So along the same vein, we have SEF2. Those are two nonmetals. So we know we just need their name, selenium. We know we need fluoride to tell us we're done naming it. So we end it with the "ide." We have one selenium, so that's okay. We have two fluorides, so it's difluoride. The next one is one of those you just need to know.
Hydrogen acetate.
Very close.
Oh man.
Let's start with H.
Is it acetic acid or
Acid. And so, you were halfway there, Frank, when you said acetate. Which acid do we know that looks a lot like acetate? Acetic. So we take that name, all of those are going to end in ic. We take its base name. You add nitrate, becomes nitric. Sulfate becomes sulfuric. Phosphate becomes phosphoric. So acetate becomes acetic. So here we have acetic acid. Back to Frank, what does that AQ mean for the next one?
Aqueous, it's going to be an acid.
There you go. And it's going to be an acid because it has the H,
Yeah.
right? Just because you're aqueous doesn't mean you're an acid, but if you're an H with an acid, or H with an aqueous, you're an acid. Okay, so who is it, Frank? There you go. Hydro.
Hydrogen, hydro, iod.
Iodic? Yeah. No, that's fine.
Iodic, okay.
Right, but it's actually hydroiodic, and that, you know, because sometimes when you smash names together, you change the pronunciation just a little bit. So instead of iodic, it's hydroiodic. Just a saying. So it's hydroiodic acid. And then this last one, that G, of course, means that it is a gas. So it's not dissolved in water. So this is not an acid now. So this one, because there's only one way that this can exist, it's one of the quote exceptions to this whole like mono, di, and tri stuff. This is just hydrogen sulfide. What did I just do? Hydrogen sulfide. Okay. So there we have.
I missed one at the top. The
I did.
CO3.
All right. That one's for you then, Sonia. What do
Oh
we got?
man.
We'll just ask you.
Potassium.
Okay. Potassium. And what's CO3?
I don't know.
You know part of its name. What's part of its name?
I don't know. Carbonate?
There you go, right? You knew part of its name already because of the carbon, right?
Mm-hmm.
So one of the things that I really want to encourage you guys to do, nomenclature is a very scary part of this class. You're learning a new language. You are, fumbling around with the early stages of like, how do I say cup? How do I say spoon? That's okay. But you shouldn't throw your hands up like you don't know anything, because you do know some things. You knew that there was a carbon there. You knew part of that name was going to be a carva something.
Mm-hmm.
So I want you guys to take solace in the fact that you do know actually a little more than you think you do. You have the clues left and right throughout these things.
Mm-hmm.
PO4, you should know by now that Fe is iron. And you're like, oh, this PO4 thing, I don't know anything about it. Yes, you do. You know that it starts with phos. And the question is it phosphide? That would be if it's all alone. Is it phosphate? you know? So you actually know more about this than you realize you know. And I really want you guys to try to sort of rest in the fact that you do actually know more about this than you think. Now, I'm also going to give you guys a hint, a big, big hint. We did all these on the left-hand side. And then we got to the right-hand side. And we were kind of like, I don't really know. Except that some of the stuff on the right-hand side comes from the left-hand side, meaning there are hints, there are clues over here on the left-hand side that we could have used on the right. And vice versa. So when we did this one, I think, Frank, was it you with the phosphate or who did the iron phosphate with me? No one's going to fess up to that? I forget who it was. But we said we knew there was iron. We knew there was phosphate. And we're like, well, shoot, I can't remember the charge on phosphate. Well, look right here. On this ammonium phosphate, why in the world would I put a 3 here? It's right there. I put a 3 there because this is probably a -3. Otherwise, there'd be no reason to put 3 ammoniums there. So then you go like, oh, well, if that's somewhere, now I know that the phosphate is a -3, then that iron must have been a +3. Now, I failed to put a sulfate over here for us, but let's just say that I had COSO4. And I asked you to name this compound. My bold Frank will do this one with me. What do you know about this compound?
We got carbon.
Cobalt.
Or cobalt.
That's fine. And what do we have? What's this guy?
Shit.
Ready? This is what I'm trying to point out.
We need 4 of these.
No. Look at what I did, Frank.
Look on the left
Look at
side.
what I did. Hey, who said that?
Sonia.
Sonia, yeah. On the left-hand side, I saw this SO4. I'm like, well, shoot, I don't know what that, oh, I do know what that is. Why? Because Forrest told me. So you look over there, you go like, oh, wow, okay, yeah, okay, I forgot its name. Oh, wait, I see it. Oh, wait, someone already gave me its name. So I know that it is a cobalt sulfate. But the problem is, does cobalt behave?
No.
No, it does not. So you got to tell me which cobalt it is. Oh my goodness, there's no way that I can know that charge on the cobalt because I forgot the charge on sulfate, didn't I? Yeah, I did. Is there a clue anywhere on that left-hand side to tell me the charge on that sulfate?
The charge of the iron is going to be the opposite of the sulfate.
That is correct. What's another place that you can have that hint? Look at that sulfuric acid. Why do you think I have 2 H's there? Every single one of these compounds is designed to be balanced, which means all of the charges have canceled each other out. So if there's 2 hydrogens, what's the charge on hydrogen?
1.
1. So if the charge on hydrogen is 1 and there's 2 of them, then the left-hand side of this compound right here is a +2, which means the sulfate has to be
-2.
-2. So then we come right back down here and say, well, if that's a -2, then this cobalt must be a +2. And so what I'm trying to get at here is when we come to exam time, I have no choice but to give you these hints. There is no way around me not giving you these hints. Because I will have written compounds somewhere on that test that have to be right. Otherwise, you can't do the problem. So if I've written it down, that thing is written correctly. You can gain hints from that. So some other hint that could maybe show up is if I had something like 8NO3, which I'm sure you all remember, of course, is nitric acid. But maybe that nitric acid shows up somewhere to where you get up here and you're like, okay, calcium nitrate, shoot, I can't remember the charge on nitrate. I know calcium's a +2, it's on the periodic table, but I'll be damned if I can remember what nitrate is. And then somewhere else on the exam, you see nitric acid. What's the charge on nitrate? Frank. Figure it out. What's the charge on that nitrate, given that that is correct?
-3.
-1. And why is that? Because it has how many hydrogens?
I only see 1 hydrogen.
That is correct. So if this half is a +1, then this half is a
-1.
-1. And so look, now I know, oh, that's right. If calcium's a 2+ and nitrate's a -1, I'm going to need 2 of them to do it. So as we start to approach the exam especially, I want us to be mindful that there's almost no way that I can avoid giving you guys hints, giving you guys clues as to how to do the nomenclature. Because if you forget some of your polyatomics, they're probably going to be used somewhere else as part of an example. And you'll be able to glean that information from there to help you. What's the chart? Look, Frank, look at this. Ready? Because I know you'll talk to me here. Look at this. Acetic acid. You said there's something like an acetate in there. Great. What's the charge on acetate?
I don't know.
Yes, you do.
Okay.
Frank, you do know.
Okay,
On the
so
left-hand side, what do you see?
a hydrogen. Okay.
What's the charge on hydrogen? So then the acetate must be a -1. Yeah, it's got to be a -1. So when we look at these, just be mindful that there is no way that I can avoid giving you guys those hints.
Now I'm a little confused because okay, so we have acetic acid right here, and you just cut it off at the hydrogen, but how do I know where to cut it off? It's like we got hydrogen, and then we got
Right.
we got carbon too.
No, I get it. So if I have HCl and HF and HBr, and sorry, let me rewrite that there. HBr and I don't know, H2S, and make sure all these are AQs. What makes something an acid? It must start with H. So this is pretty intuitive. Where do we cut it off? Right after the H. There's no difference between that and HNO3, H2SO4, H3PO4. We're going to cut it off right at the H, which is why we write acetic acid as HC2H3O2. They're written this way to say, this is how many H's this acid is going to give us. The rest of it is the other part. So that's how you know. Or that's how you will know when you get more familiarity with them. Oh my gosh, all these hints. Christmas comes early. Okay. Revisit single replacement. Okay, so we have copper plus silver nitrate. We'll go to make, and I would have to tell you this one because it's a transition one. Copper 2 nitrate and silver. We recognize this as a single replacement because one person is standing all alone and is going to come and steal the other person's group. On the other side, the silver has to now sit out. Is this balanced? I think Juan will probably tell me no, because I thought it was, or no, Julio. Where's Julio? Oh, it was Julio last time. All right, well, Juan, you're gonna have to step in for Julio now. Is this balanced as a reaction? All right, Bella, jump to the front real quick. Bella, can you help me out?
No, it's not balanced. There's
Okay.
2 nitrates on the right side and 1 on the left side.
Right, so she sees this, she keeps the grouping, right? She goes, there's 2 on the right and only 1 on the left, so she's gonna tell me to put a 2 in front of the silver. So what does that do to our silver?
And it unbalances the silvers, so then you have to put a 2 on the right side in front of the silver.
All right. Ooh, whoa, what just happened? That was weird. Oh, my palm slipped off my little thing and just everything went to haywire there. All right. So now we have a balanced equation. And just a little how do you do? All right. Now we have this reaction. Somebody pop something over here in chat. Oh, all right, Juan. Thank you for the heads up. All right. So we do this reaction. That's kind of cool. We do this reaction. Oops, let me get a solid on there. We get a little solid silver and this copper 2 nitrate. Nothing doing. Now you might look at that and go like, wait, I don't understand. We basically have the same ingredients. Why does one reaction happen but the other one not? I'm glad you asked, Laura.
That's exactly.
So, say that again, Laura?
I said that's exactly what I was thinking.
Yeah, I know. Well, this is your question from before class. So this is because we have something called the activity series of metals. The activity series of metals. Now, this activity series is basically saying some metals are more active than others or more reactive. Some metals are more reactive than others. Not all metals are the same. We clearly know that just from our own personal interactions. Iron is not the same as lead, is not the same as gold, is not the same as copper. There's a reason they have their colors and their physical properties, and even now their chemical properties. All right, what I'm going to do is, this is where I would say something in your thing of like, I need at least 6 lines of your notes plus a space in between. So give me like 9 lines in your notes. Here we go. I'm going to write the activity series of the metals here for you, broken up into 3 sections. And we're going to talk about those 3 sections. So let's see. I'm going to start with, that'll be that. All right. We'll go with lithium is more reactive than potassium, which is more reactive than barium, which is greater than strontium, which is greater than calcium, which is greater than sodium, which is greater than magnesium. So lithium is really, really reactive. It's more reactive than potassium and barium, etc. down the line. All right, new line, leaving ourselves some room. Magnesium is greater than aluminum, which is greater than manganese, greater than zinc, greater than iron, greater than cadmium, greater than cobalt, greater than nickel, greater than tin, greater than lead. Don't worry, we'll have time to, I'll give us time to write this down.
Is this just a need to know, or is there some like common sense to the, or like some way to figure this out? Or is this just one of those things we're gonna have to memorize?
The only thing I've ever said you have to memorize in this class is nomenclature. I will show you something cool about this. You're probably already seeing it, Miguel, or you will by the time I ask. So I'm gonna put you in my back pocket for the how do we use it type thing. So get ready. All right, I need a little more space in another line. We need that lead is greater than parentheses hydrogen, which is greater than copper, which is greater than silver, which is greater than mercury, which is greater than gold. Okay. Now this activity series goes like this. The metal, quote, before replaces the ion that comes after, or the aqueous. Whoever's swimming around. So if you are that elemental metal coming in, will you or will you not replace the one that's already swimming? Will you take its dance partner and go swimming and make the other one sit out? Here's how it goes. Let's take a look. On our first reaction, first let me just make sure you guys have that written down. So I'll give you guys a second to make sure you have that. Let's see, is Sarah in the house?
What up? AG. I'm sorry, the purple line after AG, that element.
Oh, sorry, H. You were breaking up, but I think you want me to rewrite this a little better. Is that what I'm getting on?
Yeah.
Okay, cool.
I'm here, Pippin. What's popping?
Oh no, I was just making sure because usually you're the one like scroll up, scroll up, scroll up. So I want to make sure you're here.
Oh yeah, I missed the second little revisit single replacement line, but I wasn't worried about it. I'll just go back and get it earlier. Yeah, that one. There we go. Yeah.
Well, we're gonna get there. So I just wanted to make sure you had that reactivity series, or the activity series, I should say. So what I want us to do is I want us to use this activity series we just wrote and look at these two different reactions and why one of them will work and the other one won't. So we look at this reaction and we see copper, solid copper, and an aqueous silver, or an ion of silver. So I want to come back down to this reactivity series and ask myself, does that metal show up before that floating around silver ion? So we come down here, we go like, all right, silver, where are you? Nope, you're not there. Keep going, where's the silver? Oh, or sorry, we're looking for the copper, sorry, the copper. We're looking for the copper metal. Copper metal is right here. Is that copper before the silver? It is, so it will replace it. In the second one, we switched their places. Silver being the solid, copper being the ion. Silver does not come before copper. It will not occur. Now, for those of you who have already started the reactions lab, this is in your lab. You will see that this former with a copper metal and the silver nitrate will do a reaction, but I could have very easily done this oppositely and nothing would have happened. Now, let's take a look at your other reactions here real quick that we did last time for our single replacements. We have magnesium trying to kick out hydrogen. Do we see magnesium metal before hydrogen? All right, let's look. Do we see magnesium here before hydrogen? Yes, so that's gonna work. Let's take a look.
So is this one, that's one continuous line then?
That is one continuous line. I've broken it up for a reason, and you're gonna help me with that in just a second. Again, potassium trying to kick out the hydrogen. Does that work? Oops. Does that work? Of course, we see potassium well before we see the hydrogen. Now, let's go ahead and make up some other ones here just for kicks. Will it work? Let's do magnesium with tin 2 chloride. Will this go? We look up at our chart. We find our magnesium. We find our tin. Magnesium is before tin. This will go. What if I have zinc plus sodium chloride? Will that reaction go?
No.
No, because we see zinc here, which is not before the sodium. So if I drop zinc in a bunch of salt water, nothing is going to happen. If I drop magnesium in a bunch of tin chloride water, something will happen. Okay. So here's the deal. Miguel says, do we have to memorize this? I will tell you right now, no. So you're going to give this to us on the exam? No. Well, then how are we supposed to use this? Miguel, help me out.
Okay.
Everything in orange. Can you see a pattern with them?
They're all in groups 1 and 2.
Nice. These are all groups 1 and 2. What about the guys in blue? Who are they?
They are transitions.
There you go. These are transition metals. All right, this one's a little harder, but maybe you know the names of everyone in purple.
Mm-hmm.
Okay, they actually have a name. We've actually used their name before. They share their name with certain gases.
Noble.
Yeah, the gases share it with them. Yes, these are the noble metals.
Okay.
So really, what does this come down to? This really comes down to this. Groups 1 and 2 are greater than the transition metals, which are greater than the noble metals. And so what I will expect of you guys is to know that. Not the ins and outs of the in-betweens. Not, oh, is it cadmium versus manganese? You know what? I don't even know. I would have to walk up to this thing and go like, no, cadmium is not more reactive than manganese. I would have to have the chart. But what do I know? Groups 1 and 2 beat everyone. They're more reactive than transition metals, and those in turn are more reactive than the noble metals. Do I know the subtleties in between each of those? No. And in fact, if you look at the groups 1 and 2, you notice that poor little sodium here comes after 3 of the group 2s. Why isn't it with its group 1? I don't know, but it's not. So on the test, you'll have to recognize a pairing and realize, okay, is it a group 1 and 2 with a transition or noble? Okay, we're gonna go. Is it a transition metal with, okay, now we have to pay attention. Is it trying to kick out a group 1 and 2, or is it trying to kick out a noble? If it's kicking out a noble, we're fine. If it's a noble trying to kick anyone out, it ain't gonna happen. So did I answer your question there, Miguel?
Yes.
Yeah. So, why are they called noble metals? Why are they called noble gases?
Because they don't react.
Because they don't react. Now remember, I said the noble gases were actually named after the noble metals. So if noble gases don't react, then guess who else doesn't react? The noble metals. How do we know that? We go back into Mesopotamia, we dig around in the dirt, we find an old burial site. What's basically the only thing you're going to find in that burial site?
Gold.
Gold, silver, copper, right? You aren't going to find any of their iron tools. They've rusted away. You're not going to find anything made out of lead. It's all dissolved away. You're only going to find these noble metals that never reacted, that just sat in the ground and just waited for you and waited for you. Now, these are actually defined, and I'm, no one called me out on this parentheses H. The parentheses H means we had to define it somehow. And what we did is we defined it in reference to essentially, will it dissolve in hydrochloric acid? Will it dissolve in a solution that contains an acid like that? And actually a specific strength, I think it's 0.1. We'll talk about that a little bit later. But this is kind of cool because since we're all having a good time today, I'm going to fix this arrow and tell you a little story. What are locks made out of? I don't mean the water lock. I mean the thing that you secure your stuff with.
Steel, I guess.
Which usually made out of, steel's made out of iron, right? So imagine you're a thief back in the 1500s and you're breaking into some noble person's house to pick open the lock and get some money so you can feed the village. You go in the first night, you can pick the lock, not a problem. The local monarch there gets a little upset has the lock maker make a slightly better lock. You come in the next week, you try to pick the lock, you can't. So how do you get the chest open? You certainly aren't going to just break it open. That'll wake everyone up. You take some acid. Yes, put it on the lock. It'll dissolve, or I should say the iron will replace the hydrogen. So it'll slowly start eating away its own self. Pretty soon the lock falls apart. You open up the chest, you get the money, you feed your village. You come back the next week. Because, man, you're kicking ass and taking names, right? They've changed the lock. You're like, not a problem. I can pick this. You can't pick it. You're like, well, that's okay. I got my acid. But that lock looks a little funny. It looks a little bronzy or coppery. You're like, that's okay. Put your acid on there. Is your acid going to dissolve that copper?
Negative.
Negative, Ghost Rider. And so you wait and you wait and you wait and you fall asleep. And you wake up the next day in shackles. They have caught you. Now, that's a neat little story because I was actually watching one of the History Channel things years ago, and in one of the little burial things was a copper lock on the chest of this person that was buried. And I still remember the narrator's like, oh, and we don't know exactly why it was made out of copper. And I'm like, I do. I know why they would take the time to spend that much money on a copper lock. So you know, if it's strong enough that the thief can't pick it, they also can't dissolve it with acid. Now it's kind of cool. Story time number 2. Look at this little PB. This PB is sitting right before a little H. What does that tell you about lead versus H? Will it react?
Yes.
Yeah. So what happens if you have some lead with some good old water? Will that not have the chance to do something like this? Lead. Why is it symbol PB? Anybody who speaks Spanish and thinks about it might actually know. Anybody here speak Spanish? Giselle, okay. Do you happen to know?
No.
Oh, you don't? Okay. I just saw your mic pop up, so I thought maybe you did. Does anybody happen to know?
I said plomo, but I'm not sure.
Oh, that's exactly right, Giselle. You absolutely right. Thank you. For once, somebody got it on the first try. Plumbo is the word for lead in Spanish, which of course is where we get all that from Latin, right? Plumbo. That's why it's PB. That's why it's not LE. Plumbo, PB for lead. What else sounds like plumbo? And Frank, don't say plum.
No, I remember it peanut butter, and like when I finish eating a peanut butter sandwich, my tummy feels like lead.
Fair enough. But what else sort of sounds like plumbo?
Plumbing.
A plumber?
Plumbing, right? How do we get the term plumbing? We get the term plumbing because if there's one thing that the Romans were great at, it was building aqueducts. It was building things to take water from one place to another. A lot of those aqueducts were either open air aqueducts, or eventually when they started to get to the city, they would actually carry the water to different places using pipes, which we later call plumbing. And the reason why we do that is because those pipes were originally made out of clay. But over time, as people and horse-drawn carts and everything rumble over the top of the dirt where these pipes are buried, those poor clay pipes will break. So what do? Well, the Romans knew something. Lead has a very low melting point and it's a very soft metal. So all you do is you heat up the lead a little bit, you get it all nice and liquidy, you take a little swab, you dip it in the lead and you run it down the pipe, it cools, it hardens. You've now lined the inside of your clay pipes with lead. Now a horse-drawn carriage or a person steps on it, it breaks the clay, but it merely bends the lead. And now your pipes don't rupture. But does anybody see a problem with this? Over enough time, guess what ends up happening? This lead gets into solution. And what do we know about lead and the human nervous system?
Messes it all up.
Oh, yes, it does. And so lead pipes were used for a long, long time. Even as much as 100 years ago, we were still using lead for pipes. Very easy to mine, very easy to melt, to shape, and everything. The problem was everyone's getting lead poisoning. So you don't find lead pipes anymore. You'll have galvanized pipe, galvanized steel. You'll have copper. Now we have that wonderful PEX stuff. No more lead pipes. We don't want that in the water supply. So at the end of this, what do I need to know? Going back to Ms. Bain's question before class. In the lab, it's asking you, hey, if you have these reactions or these pairs of things, how are we supposed to know if it'll go or not? What you want to do is you want to look at the metal. That one right here, usually in front, and say, hey, does that metal replace the aqueous solution? So you just run down this, essentially a long number line that I've broken up for you into 3 groups and say, look, does potassium come before sodium? Yep, okay, it's going to do it. Does nickel come before aluminum? No, it won't work. And that's how you use that chart. For us on the exam, it's going to be noticing these trends. Is it group 1 and 2 versus transition versus the noble metals?
So would the answer just be reaction, or would you write yes?
Yeah, I would just write yeses and nos because that was the question.
Okay.
I think, if I recall correctly. If it asks what the products are, then what you would do is you would say, okay, it worked, great, let's go ahead and do it. It didn't work, just write no reaction. But I forget the exact question on it. Is it asking you yes or no, or is it asking you what are the products?
It says indicate which of the following reactions would occur.
Yeah, then that's just a yes or no.
Okay.
Okay. So that's the single replacements. I promised you that we would talk about the double replacements today because we need to know who is the one that is actually going to be the solid. Who's the one that's going to be sitting out when they do the reaction? So let's revisit double replacement. Revisit double replacement. All right. So who will be the PPT? All right, we got some rules here, guys. These rules are called the solubility rules. There's 7 of them, and we're going to apply them in the order in which they are written. And we're going to take a look at some of the reactions that we have done, and I'll put a couple of others. And we'll see if we can figure out who is going to fall out of solution and who's going to stay swimming. All right. So here we have the solubility rules. I should note that we're going to apply these in order. All right. Rule number 1. All sodium, potassium, and ammonium are soluble. If you have sodiums, potassiums, or ammoniums in there, you will be soluble. Rule number 2. All nitrate, acetates, and perchlorates, these two are soluble. So if you have a nitrate, an acetate, or a perchlorate in there, it will make sure that it goes into solution. Rule number 3. All silvers, mercuries, and leads are insoluble. And that's actually both versions of mercury and both versions of lead. Number 4. All chloride, bromide, and iodides are soluble. Number 5. All carbonate, oxide, sulfide, hydroxide, phosphate. Woo. Insoluble. Number 6. All sulfate, except calcium and barium, soluble. And finally, if not here, assume insoluble. Whew, that's a lot. Give you a second to catch up. Okay.
Is there a reason they're written in 6 different rules if 4 of them are all soluble and 2 of them are insoluble? Why didn't they just?
Because we have to do this in order, and I'll show you what I mean by that. In hopefully either the examples we did or the examples we're going to do. So, and it especially comes down to this one right here. This is the one that is the crucial one, because these two are just it kind of doesn't matter the way in which you apply them, but it really comes down to this guy and the last one that is the deal breakers here. So we have to go in order. So let's see, who are my people that normally want this written? We got the Sarahs and the Ellens and the Lauras. You guys got these?
Yes.
Not yet.
Okay. Let me know when you got it, Ellen, because I'm going to
All right.
rely on you guys' notes to do this. because I'm going to go back to the ones that we did here last time. All right, double replacement. Let's take a look. Sodium chloride, are you soluble or insoluble? Forget the fact that I've already told you. Let's just look at each of these compounds. Will sodium chloride be soluble or not?
Yes.
Why?
Sodium.
Sodium. So the way we do this is we take a look and we say, hey, in order, sodium, are you soluble? Oh, you're the first rule. Yes, soluble. You don't even have to worry about the rest of that compound, because if one of these will swim, the other will swim as long as it's before the other one. You'll see what I mean in a second. All right, sodium swims. Oh, you know what? Let me just make that very clear here. Sodium swims. If you're with sodium, you will be floating around in solution. There is no ifs, ands, or buts about it. It's just like when you're learning to swim and you're sitting out there and you're kicking your feet and everything, and mom is holding your hands. If mama lets go to go swimming, you'd better start swimming or it's going to be a bad day, right? If one of you goes swimming, the other one better go swimming. Never mind that she has her hand on your head holding you under for some unknown reason. Dear diary. Oh, sorry. I blanked out there for a second.
I have no
All right.
response to that.
Oh, Meng from downtown. I love that. All right, silver and nitrate. Will this be soluble? Let's go back to our rules, and this is where it'll come in for you. The question is, do we see silver? Check.
No.
Right here on rule 3. Do we see nitrate? Check. Does nitrate trump silver? Yes. So silver nitrate will be soluble.
Got it.
What's that on rule 5 after the second to last one?
PO43 minus, OH minus, hydroxide.
Oh, there we go.
So Miguel, that's the reason why we have these in the order we do. While silver does not want to be soluble, it got paired with the nitrate. And the nitrate says, sorry, I'm ahead of you. I'm going to go swimming. You are going to go swimming.
Yeah, it makes sense now. Thanks.
Right? So let's take a look at the next. Sodium and nitrate. Are you going to be soluble or insoluble? Cadence. Wait, no, Cadence doesn't talk to me. Plasma. Is sodium nitrate? Yeah, why?
Because it is sodium.
That's right, because sodium swims. And oh, look, nitrate also wants to swim. It's a winning combination. Silver chloride, Basma. Does that want to be soluble? Let's go back to our chart here. We see silver, you don't want to be soluble. We see chloride, you do, but who's first? Silver was first.
So it's insoluble.
Right, so now that's why it's insoluble, because the silver came before the chloride. Listen, chloride, bromide, iodine, great ways to get anything into solution. Well, except those 3. The halogens are great. They're salt forming and salts dissolve, remember? Salt forming, they'll dissolve everything. Oh, except silver and mercury and lead. If you want those guys to go into solution, nitrate's your guy. Pair them up with the nitrate and they'll go swimming in solution. All right. MgCl2, soluble or insoluble? Well, let's go back. Let's see, do we see magnesium? Oh no, we don't see magnesium, so that says it should be insoluble. Except we see a chloride which says it will be soluble, and that soluble comes before the insoluble. K3PO4, soluble or insoluble? Well, potassium looks a lot like who? Actually, be like whom, actually? Somebody say something that potassium might look like. So many choices.
Sodium.
There we go. So potassium looks like sodium. Sodium swims, potassium swims.
How did you jump from potassium to sodium?
Group 1. And the fact that it's also in rule 1. You notice that sodium and potassium are in group 1. Ammonium is a little bit odd because it's the polyatomic, but the other one that could be written here is H. They're all in the group 1. And those group 1s love to go swimming. We don't mention H because H comes a little later in acids, and we don't usually go below potassium because we're usually not going to be using stuff like cesium and francium and things. So we're giving you the common ones that would be made here. But look at that, group 1s, they want to go swimming. So even though the phosphate down here says, no, I don't, the potassium wins. Oops.
So if it's not on the list, but it's in group 1, then it's soluble.
Well, group 1 is, well, okay, yes. I probably will not do that to you because when's the last time you heard of rubidium, cesium, or francium? You haven't, and you won't. So I'm giving you stuff that I would be using in compounds.
Okay.
So check it out. So we know that the K3PO4 is soluble. Hopefully by now you know that KCl is soluble because of group 1. So therefore, check it out. Magnesium and phosphate, of course, is going to be the solid because phosphate is insoluble and magnesium isn't even here, both of which say we're going to dump out and be a solid. So as you look at the pairings, as you look at these, and in fact, let me be very clear because I know that at the very least, Frank is losing his mind saying, how am I supposed to know this entire thing? I'm going to have to go do some sort of voodoo ritual to make sure I know this. Not really. Just like with the activity series, some of these are going to fall out. As Laura just said, group 1 and ammonia going to be soluble today. Group 1 and ammonia soluble today. Hey, I just made up a song.
I'm looking at rule 6 and okay.
Hey,
so
I'm not at 6 yet, man. Hey, Frank, walk with me.
Okay.
Walk with me. We're getting there. I got things for everything. I just made one up for number 1. You can sing it to yourself, Frank. Group 1 and ammonium soluble today. That's going to stick in your head and in the chest. All nitrates are soluble. All nitrates are soluble. That is a workhorse to get anyone else into solution. We already know that the halogens, the salt formings, almost uniformly are soluble because salts dissolve in water. Well, except these guys. All right. Silver, mercury, and lead don't play ball with people. You know that because lead pipes. You know that because silver doesn't react. Well, what about gold? Correct. Gold also doesn't want to do this either. But these guys especially. All right, down here, number 5. How am I supposed to remember all these? Well, if we pay attention to all the examples that I use throughout this class, with carbonate, I've often but put CaCO3. Is that soluble or insoluble? Even without this list, if we set the Wayback Machine, I routinely referred to calcium carbonate as chalk or marble. Is marble soluble or not?
No.
No, we use it for countertops to get wet all the time. Oxygen. You see me write Fe2O3 over and over again. What is Fe2O3?
Iron oxide.
Okay, iron oxide.
Rust.
Rust, right? And does rust dissolve in water? If it were that easy, we'd be able to keep all of our metal stuff nice, right? We set the Wayback Machine again. I think it was FeS2, pyrite, fool's gold, sulfides. Oh, look, and wait, aren't you guys like the same? Aren't you guys the same? Aren't you in the same group, same family? So of course you're gonna do the same thing. Hydroxide, less intuitive, but phosphate shouldn't be that bad. Ca3 parentheses PO4 2. Calcium phosphate. I've said it once, I've said it 4, 5, 6 times. In one form or another, calcium phosphate is comprising of your your bones. Do your bones dissolve in water? I hope not.
No.
I would say no, considering we're bags of mostly water. That'd be bad. So even number 5, with all of its glory here, if you just think about the compounds that I have used over and over again, you'll have a sense for who would be soluble and who wouldn't. When you do the labs, when you do the homeworks, you'll start to get this feeling, oh yeah, I see these over and over again. So how do I get phosphate into solution? I don't know. Put it with an ammonium, right? We'll get that in solution. Put it with a sodium phosphate, erroneously called trisodium phosphate, or TSP, if you go down to Home Depot. They're totally misnaming it, but hey, somebody marketed it, and there you go. How do you get sodium into, phosphate into solution? Pair it with sodium. How do you get carbonate into solution? Pair it with potassium. You want to get iron out of solution? Put it on a phosphate, drop it out. How do we get calcium into solution? Stick a nitrate on it. So all of these that we've been using, if you start to just sort of like look and sort of get the feel for it, you'll notice that these aren't so different. Now, Frank, you asked about number 6.
I asked about number 6. So
yeah.
It's all sodiums are like, it says all sodiums, but in the parentheses says except something. But
except calcium and barium.
Except calcium. Okay, but it's like I'm having some trouble drawing the connection between calcium, barium, and sodium.
SO4 isn't sodium.
Oh, it's not.
Oh man, from downtown, Miguel doing a little Frank speak there. Thank you, Miguel. I love it when my students get together to study. I love it when they start to understand how each other think, because it really does help. This is why I set study groups, guys. You guys really get to help each other. Well done, Miguel. Now the sulfate, sulfate is used actually quite a bit, because you notice that its only exceptions happen to be calcium and barium. Sulfate shows up in a lot of places. Magnesium sulfate is your Epsom salts for your bath. So magnesium actually will dissolve, but as soon as you get to calcium and barium, the solubility drops off and it becomes insoluble. But I always remember sulfate, because sulfate sort of sounds like sodium. They're sort of the same, and sodium swims, so sulfate swims. I love alliteration. Sulfate sort of sounds like sodium. Sodium swims, sulfate swims, well, except for these guys. And by the way, calcium sulfate is one of the other things that can be used as chalk. So calcium sulfate is also another thing that is used as chalk. Calcium carbonate and calcium sulfate, both are used as a chalk material because they don't dissolve.
And that would be insoluble because the calcium is before the sulfate?
No, because the calcium is not even on there. And the exception shows up within the sulfate's definition. So you look at calcium sulfate and go like, well, calcium's not here, it's insoluble. Like, oh, a sulfate, you're soluble. Oh, wait, parentheses, except this guy. In fact, maybe I should actually highlight those and just say, look, except these guys, sulfates will be okay, except those two. Now, again, the one thing I want to encourage you guys as we start looking at these is I'm not going to be here to try to beat you up and ask you super trick questions here, right? This is an intro chem class. You're not going to have this chart. I'm going to expect that you will have picked up through the lectures, through the labs, through the homeworks, all of the common ones that repeat over and over and over again. I mean, if you look at the reactions that we did last time, who shows up a lot? Sodium and potassium to get things floating around. Who shows up a lot? Nitrates, chlorides showing up a lot. Oh, look, hydroxide. Why are you aqueous? Because you got stuck with the potassium. Look who shows up. Carbonate shows up a lot. So what I want to encourage you guys is to not be afraid. Acetate, look at that. Carbonates, look at that. So I don't want you guys to be like, oh my gosh, there's so many things. Well, there aren't if you see how these things are presented, because we keep coming back to these workhorses. Yes, trust me, there's a lot more solubility rules than this, and there's a lot more exceptions than this, but we aren't going to see them. These are the common ones, and you'll see that even in the common ones, that I even narrowed down even more for the most common. So, you know, be familiar, but don't freak out about it. Just know that that these lectures, the homework, the labs should prepare you pretty well for understanding who's soluble and who's not. And let me give you one last pro tip. Oh man, I'm giving away all my tricks. Forget everything on the left. Look on the right. Who is not the PPT?
Sodium.
Yeah, because sodium swims. So in this class, the reactions will always go. You come to Chem 120, I might give you some problems where I'm like, hey, is this going to work or not? And you have to be very savvy as to whether or not someone is going to fall out of solution or not. In our cases, they will always. So in some respects, it's actually almost easier to see who's still swimming, and that'll tell you who is not. Who's still swimming, that'll tell you who is not. Because on the exam, I have to give you the left-hand side, and I have to tell you what's going on. Otherwise, you can't do the problem. So a neat little way is to figure out who's still swimming, the other one is not. Okay. Let's see. I kind of am at a weird place that I could stop because we can get through everything tomorrow in tomorrow's time. And I don't know if there's any advantage of going forward with this. Do we have any questions, or should we knock off early?
I have a slew of questions, but probably
I have so
one.
many questions I don't even know how to ask.
Okay.
Just to
Well,
work.
why don't I go ahead and just stop the recording, and then we'll figure out how to ask all these questions again and get them answered.